Okay, we're in chapter 14. This is our second video, and we're talking about solutions. So we're going to start in this video talking about how do I predict as a chemist, how can I be knowledgeable to predict whether or not a solute will actually dissolve in any solvent before I actually have to do the experiment. So can I do this prediction? Can I predict solubility? The answer is yes, to some degree. There are certain rules and trends that chemists can use or learn over time to where we can pretty much predict whether a compound is soluble or not, either in water or in another solvent. So we're going to start with ionic compounds first. Remember, if you have an ionic compound, you have full charges on that compound. Water, remember, if you want to know if that ionic compound is soluble in water, remember water is a polar compound. Water's structure is bent, and oxygen is more electronegative than the hydrogen, so oxygen has a partial negative charge and the hydrogens have partial positive charge. So water is polar. It has partial charges. Ionic compounds always have cations with full charges and anions, which are nonmetals. So metals are the cations, nonmetal anions with negative charges. So here we have ionic compounds. They have full charges. Chemists have a rule that we'll talk about in a second called like dissolves like. And most of the time, if a compound that has charges is put into a solvent that has charges or partial charges, most of the time you can predict that it's soluble. But this isn't always the case. Like dissolve like basically means charged compounds like to be in charged solvents. Uncharged compounds like to be in uncharged solvents. Like dissolves like. So you would think that ionic compounds, which have full charges, if charged things like to be inside of charged things, that ionic compounds would always be soluble in water. But it turns out that this isn't quite the case. Remember, for every rule in chemistry, there's always an exception, or more than one exception. So chemists have come up with something called solubility rules for ionic compounds. When you get to Chem 1, you'll probably actually end up memorizing these rules. That's how important they are to chemists. You'll get to the point where you know, oh, most lead ions are not soluble in water. And so you'll learn the rules. From now, though, what we have something called solubility tables or solubility charts. And we've actually looked at solubility tables and charts before in both lab and in previous chapters, so I'm not going to go over that again. But for ionic compounds, sometimes it's difficult to know whether or not it's soluble in water or not. So for ionic compounds, most of the time, chemists will either use the solubility rules they've memorized, or in our case, a solubility table where we can look up the solubility of the ion combination. If something says that it's soluble on the solubility table, so if you look up sodium chloride, and sodium chloride turns out to be a soluble compound, what does that mean? That means when dissolved in water, you form a solution. And a solution in water is called an aqueous solution, right? Because the compound dissolves in water. So we know something like sodium chloride, because all sodium cations are soluble in water most of the time, that sodium chloride would form an aqueous solution or be soluble in water. What would happen if you had a compound that, if you looked on the solubility table, it said that it was insoluble? If it said it was insoluble, that means that it would not form an aqueous solution. It would remain a solid if you dissolved it in the water. Examples of these are lead-2 ions. Like if you have lead-2 chloride, for instance, that's not going to be soluble in water. So it would be written as a solid when dissolved in water. It would remain as a precipitate, or actually as a solid. It would not dissolve at all. It's insoluble. So for ionic compounds, if you want to know whether or not the compound's soluble in water, you're going to have to use a solubility table. What about the rest of the molecules that exist that are not ionic compounds, the covalent compounds? We can predict their solubility using the trend like dissolves like. Look at the nature of the solvent and the solute. If you have a covalent compound. Remember, covalent compounds or molecules only contain nonmetals. If the 3D nature of that molecule is polar, then it will dissolve in polar solvents. Polar compounds dissolve in polar solvents. Remember, polar means to have partial charges. If you can't remember what a polar compound is or how to predict it, whether or not something is polar based on its molecular structure, you're going to need to go back and look at Chapter 11. Alright? I'm not going to go ahead and lecture over that again, but if you don't know what the difference between polar and nonpolar is, I strongly suggest you go back and read that part of Chapter 11, Polar and Nonpolar Compounds. But polar compounds dissolve in polar solvents, and nonpolar compounds typically dissolve in nonpolar solvents. To be polar means to have partial charges. The charge distribution throughout the electron distribution throughout all of the bonds in the compounds is not equally distributed. It's polar. To be nonpolar means to have no partial charges. No partial charges. So, what are some examples of polar compounds and nonpolar compounds? Usually when you have an electronegative atom, such as oxygen, nitrogen, fluorine, chlorine, you're going to have a polar compound. It's easier to know when you have nonpolar compounds. Nonpolar compounds are usually either compounds that contain the same atom bonded to each other, like chlorine, Cl2, oxygen, O2, nitrogen, N2. So those are all nonpolar because they have equal electronegativities. The other class of nonpolar compounds are a class of compounds called hydrocarbons. Hydrocarbons are a class of compounds where their molecular formula is CXHY, meaning they only contain carbons and hydrogens. Why are hydrocarbons nonpolar compounds? Well, if you remember back from Chapter 11, go back to Chapter 11 if you don't remember, but if you remember back from Chapter 11, we were looking at Lewis structures and three-dimensional shapes of compounds. We talked about hydrocarbons, and we said that hydrocarbons only contain carbon-carbon and carbon-hydrogen bonds in the molecules. An example is octane or heptane or propane. These compounds only contain carbon-carbon and carbon-hydrogen type bonds. These two bond types are nonpolar because carbon and hydrogen have the same electronegativity, which means they have equal pull for electrons shared in their chemical bonds. So if you have equal pull, you're nonpolar. So in general, hydrocarbons, any molecule that only contains carbon and hydrogen, is nonpolar. What's an example of a polar compound? Well, one example is water. Water, like I said before, is a polar compound because it contains electronegative bonds and the pull is unequal. Oxygen is more electronegative than hydrogen, and there's two oxygen-hydrogen bonds. So the partial negative charge goes toward the electronegative atom, and the more electropositive atoms are left at the bottom. So there's partial charges here. We have a polar compound. So would a hydrocarbon dissolve in water? Well, a hydrocarbon is nonpolar and water is polar. The rule for solubility of molecules is like dissolves like. So for any two covalent compounds, polar compounds are soluble only in polar solvents, and nonpolar compounds are soluble in nonpolar solvents. So let's look at some examples here. Let's do C6H6. This compound's a solid. It's called benzene. Let's look at a compound C6H14. This is hexane. It's a liquid at room temperature. And let's look at H2O. Water, a liquid at room temperature. And finally, let's look at, sodium chloride. Well, no, let's look at something a little less obvious. Let's look at formaldehyde. Formaldehyde is CH2O, and I'm going to draw its structure real quick. Formaldehyde's three-dimensional structure looks like this. There's a polar bond here between carbon and oxygen. Oxygen, we said, just like water, is more electronegative than carbon. So there's a polar bond. This is nonpolar, but there's a polar portion and there's a directionality to the pull of electrons in this compound overall. There's a negative oxygen and a positive carbon. So this is a polar compound. So I'm going to go back. Let's see here. Okay. I'm going to go back and I'm going to label these. So this is formaldehyde, ch14-2. We said that this was a polar covalent compound. Water, we know, is a polar covalent compound. And these last two compounds here are both hydrocarbons. This is a hydrocarbon, and we know hydrocarbons are what? Nonpolar. So both of these are hydrocarbons, so they're both nonpolar compounds. Now the question is, what dissolves what? Now, first let's look at the liquids. So let's say that we're looking at hexane. Hexane is a liquid at room temperature, so it would be a good solvent for the solid compounds. Do you think that hexane would dissolve solid benzene, C6H6? Well, the rule for solubility is like dissolves like. So nonpolar things dissolve nonpolar things. Things without charges like things without charges. So these two would actually be soluble in one another. All right. Do you think that benzene here would be soluble in water as a solvent? Well, benzene is nonpolar. It contains no charges or partial charges, and water is polar and contains high partial charges. These would be insoluble in one another, which means they wouldn't mix. The solid would not dissolve into the liquid. All right. Would water dissolve formaldehyde? It seems that it might, because they're both polar. So, as a chemist, we would suggest, because they're both polar, like dissolves like, they would be soluble in one another. So I think you're starting to understand the trend. Plus, we're going to look at this a lot in lab. So, as we look at this in lab, I think we'll understand the like dissolves like a little bit more. But read up, practice those. So this is how we would predict solubility for molecules. Let's look at some other things that affect solubility. We said that temperature affects solubility of compounds. I mentioned this earlier. I said sometimes when solvents are hotter, they dissolve more of the solute. But sometimes when the solvents are hotter, they dissolve less of the solute. Well, it actually depends on the physical state of the solute versus the solvent. If the solute is a solid, generally the solubility of solids increases as you increase temperature. So we increase solubility of solids as we increase the temperature of the solvent. Alright, for instance, if I have sodium chloride, if I put that into water at 25 degrees Celsius, less will go in than if I put it into boiling water. I can get more sodium chloride, because it's a solid, to dissolve in boiling water than I can in room temperature water. So for solids, the solubility increases as you increase temperature. It's opposite for gases. If you increase the temperature of the solvent, the solubility of the gases almost always decreases as temperature increases. For example, if I have carbon dioxide, if I try dissolving carbon dioxide into water, at the lower temperature, because it's a gas, I can get more dissolved. At the higher temperature, I get less in, because it will come out of the solution, okay, easier. So less of it's dissolved at the higher temperature. So I'm going to look at something called the solubility curve here. Here I have the solubility versus temperature. We looked at this in the last video. As we increase temperature for solids, what kind of general trend do they have on a graph? Well, generally, we said that solids increase their solubility as you increase temperature. So as temperature goes from left to right on this graph, the solubility increases. Usually my solubility curves, remember the saturation limit on that line, will increase as I go left to right. So it will curve upwards for solids dissolved in liquids. The opposite is true for a gas. If you have a gas, if you look at a solubility versus temperature curve, we said that the solubility goes down as you increase temperature. So as temperature gets higher, the solubility gets lower. Do you see how this curve, as you go left to right, decreases? If you see this type of trend, if you had to decide between a gas or a solid, you would say that this solute was most likely a gas, because as temperature increases, solubility decreases. All right, and I know there's charts of these in the book. We're going to look at a chart in a second. All right, what else affects solubility? The third thing that affects solubility is pressure. Pressure, let's see here, only has an effect on gases. Because remember, gases are very sensitive to pressure changes. If you increase the pressure of the container, what happens to the solubility? Increase the pressure of a gas solution, you increase the solubility of the gas. Okay, because you're holding the gas down into the solution. Think about the gas bubbles being dissolved in solution. Because gases have a higher kinetic energy, they can pop out very easily. So when something comes out of solution, we call that boiling, or we call it evaporation. If you have a closed container, if you increase the pressure on the surface of that liquid, in effect, you hold the gas particles in to the solution. You're pushing down on them. That keeps the gas particles in the solution, and it keeps the solubility concentration higher. If you decrease the pressure, so you have a small pressure, maybe the pressure of the gas is higher than the pressure of the atmosphere, you're going to get evaporation. Your gas is going to escape from the solvent or the liquid. But here, the gas cannot escape. So gases are more soluble at higher pressures than lower pressures. Now let's think about the two of these things together. When you go to buy a soda is a carbonated beverage, right? It's got carbon dioxide dissolved in the water with all the flavors and all that good stuff. But really, you're getting carbonated water there. The carbon dioxide is dissolved in the water. Think about how we sell carbonated beverages. When you sell them, we always sell them cold or at lower temperatures. And aren't the bottles usually pressurized or stored under pressure? These are the two conditions for gases, low temperatures and high pressures, that increase the solubility of the gas in the liquid. So we have a cold, high pressurized container. As soon as we open that container, the gases start coming out. They're released because they're not held into the solution anymore. And over time, what happens to your beverage once you've opened it and lowered to atmospheric pressure? All of the gas bubbles away, right? It evaporates out of that liquid, and you're left with a flat liquid over time, aren't you? Because as you decrease the pressure down to atmospheric pressure, the gases escaped. As the temperature warms, the kinetic energy of the gas particles became higher, and once again, the gas particles escaped from the liquid. So how do you keep the gas particles in? Lower the kinetic energy of the gas, which is lower the temperature, and increase the pressure to hold them down. Does pressure affect the solubility of solids or liquids? The answer is no. So pressure only affects the solubility of gases in solution. Okay, so now what I have here is I have an example of one of the solubility curves, or one of the solubility graphs. It's solubility of a solute versus temperature. Remember, solubility is a physical constant. It's an actual number you can look up. And the units for solubility on this graph are grams of solute per 100 grams of water. So it's the amount of solute that will dissolve in 100 grams of water. Always look not only at your axes labels, but also the units. So this is grams per 100 grams of water. The water is the solvent. So the solubility number is how many grams of that solute will be dissolved in 100 grams of water at a certain temperature. And that's our second axis. Our second axis is the x-axis. It's the temperature axis. So we see that the solubility goes up on the y-axis, 5, 6, 7, and it goes up as you go to the right on the x-axis, from 20 to 30 to 40 to 50 to 60 degrees Celsius. So looking at this curve, let's just talk about the three parts of the solubility chart, the solubility graph. First of all, we have the actual solubility constant at each temperature. For instance, if I was at 20 degrees Celsius here, what would be the solubility of this solute in 100 grams of water? We're going to just follow the xy coordinate up to the line. This would be the maximum solubility, or this would give us a saturated solution. So let's see, if this is 5, this is 6, so this is 4. Maybe it's about 4.2, 4.3 grams. So here we might say that we have about, we don't have to be exact here, 4.3 grams of our solute would dissolve in 100 grams of water. So if I wanted to look up the solubility constant for the solute, I would grab this table and say, I'm at 20 degrees Celsius. If I want to make a saturated solution, I come up to the line and I say, well, I'm going to need 4.3 grams in 100 grams of water. What if don't need 100 grams of water? What if I need to make a 50 gram of water solution? Well, how much would be soluble in 50 grams? Well, if we divide 100 by 2, we divide the solution in half, we're going to divide this number in half as well. So what's 4.3 divided by 2? Let's see, it's going to be roughly 2.65 grams of solute for every 50 grams of water. All right, so that's the saturated solution. Let's see what happens as we increase temperature. If it was 4.3 at 20 degrees Celsius, what is the solubility at 40 degrees Celsius? At 40 degrees Celsius, we're going to move up. We're going to move to the left. We're going to find the coordinates here of this point. At 40 degrees Celsius, we come over, it's just below 6. So we're going to say about 5.8 grams of solute will dissolve at 40 degrees Celsius in 100 grams of water. So we were at 4.3 and now we're at 5.8. As we increase the temperature, what happened to the solubility of the solute? It became more soluble. More of it went to solution, right? So we do see that the solute has a temperature dependence on its solubility. Now, if you had to guess whether or not this solute was a solid or a gas, what would you suspect that this is? As we increase the temperature, we increase the solubility. Well, that is the solubility trend for most solids. So I would guess, just by looking at the shape of the curve on the chart, that this was a solid and not a gas. All right, let's answer some questions and just learn about how to use these charts through the question examples. Let me first finish this chart. So right here, we said the line itself represents the saturation limit. So if I have a solution where so many grams of the solubility limit for 100 grams of solvent is exactly on this line, I have a saturated solution. If I go below the line at any temperature, what type of solution do I have? If I have less than the saturated amount dissolved at room temperature, what do I have? I have an unsaturated solution. So if you find a point at any temperature, there's a certain solubility, and it's below the solubility line, then you have an unsaturated solution. What happens if you have a point above the line? So at a certain temperature, you have more than the maximum dissolved. What do you have then? Remember, there's 3 types of solutions. You would then have a supersaturated solution. Supersaturated solution. So as we answer these questions, remember these 3 parts of the curve. Alright, I'm going to erase that because we got to be able to read it, right, to answer the questions. So you can either have saturated, unsaturated, or supersaturated, depending on how much is dissolved in the solvent at what temperature. Okay, let's look at some questions here. The first one says, what mass of this compound that we're looking at here will dissolve at 30 degrees Celsius? So this is just asking us to read the chart. So here we're at 30 degrees Celsius. We're going to go up. It says what mass will dissolve. This is the maximum amount of solvent that will dissolve. It looks like it's about right on that line, maybe just below it. I'm going to say about 4.9 grams of the solute will dissolve in 100 grams of water. So about 4.9 grams will dissolve at 30 degrees Celsius. Alright, because I went back and extrapolated to the y-axis to get the solubility. Alright, let's go to the next question. It says, if a maximum amount of 8.2 grams of this compound is soluble in 100 degrees, or grams of water at 60 degrees Celsius. So let's just look and see what that says. So we're at 60 degrees Celsius. If we go up 60 degrees Celsius, and the maximum amount of solute that will dissolve at 100 grams of water, that's the saturation line, is 8.2. That's exactly what that curve is, by the way. Yeah. We're at about 8.2 there, because that's 8 grams. 5, 6, 7, 8 grams. So we're maybe about 8.2 grams there. It says, what is the maximum amount of compound that will be soluble in 50 grams of water at 60 degrees Celsius? So if we know we have 8.2 grams in 100 grams of water at 60 degrees Celsius, sorry about that, how much will be soluble in 50 grams of water at 60 degrees Celsius? So notice we're at the same temperature, but we have half the amount of water. If you divide the amount of water or solvent by 2, you divide the amount of solute by 2. So what's 8.2 divided by 2 basically? It's 4.1 grams. So the answer will be half the amount, or I'm sorry, did I say 4.2? I meant 4.1 grams will dissolve in half the amount of solvent. All right. We discussed that one earlier with the previous example. Okay. Let's look at the next question. It says 6 grams of solute is dissolved in 100 grams of water at 60 degrees Celsius. Let's go ahead and find that. So it says 6 grams of solute in 100 grams of water. So that's the grams per 100 grams. Let's find 6. There's 6. What temperature are we at? 60 degrees Celsius. So I've got 6 grams, and I'm going to come over to 60 degrees Celsius. This is the point I'm talking about. So it says we have 6 grams of solute dissolved in 100 grams of water at 60 degrees Celsius. The solution is allowed to cool to 25 degrees Celsius. Now, what does that mean? We're going to change the temperature. So we're initially here at 60 degrees. We're going to cool from 60 down to 25. That's right here, right? Because this is 30. So this is about 25. So we're going to cool the solution down from 60 to 25. Let's see what remains in solution. Does the solute remain in solution, or does it drop out of solution at this temperature? It says no crystals form, which means nothing precipitates or drops out of the solution. So the solubility remains constant. So I'm going to go down here to 25 degrees Celsius, and I still have 6 grams of solute in 100 grams of water at 25 degrees Celsius. Alright, the solution that we just formed, this solution right here, 6 grams in 100 grams of water at 25 degrees Celsius, is that a saturated solution, an unsaturated solution, or a supersaturated solution? Well, let's look at it. I'm going to remark it. There we go. Okay, so here's our point we're looking at here. Okay, I'm going to get rid of everything else so it's not hard to see. So we're at 6 grams at 25 degrees Celsius is currently dissolved. We know that our saturation limit at 25 grams is about what? I don't know why that keeps happening. I think I totally just deleted that. Okay, sorry about that. I don't know what happened in my image, but I got it back. Ha! Alright, so our saturation limit, a saturated solution, would contain about 4.5, is that right? Yeah, 4.5 grams of the solvent at 25 degrees, solute at 25 degrees Celsius. We have 6 grams dissolved at 25 degrees Celsius. So we have more solute dissolved than should dissolve at that temperature. Remember, that's the definition of a supersaturated solution. Remember, we drew the green up here and we said if your point's anywhere up here above this line, then it's a supersaturated solution. So the fact that no crystals formed and we kept everything in solution tells us that we're supersaturated. Now, what if at this point, the beaker had been disturbed that had contained the solution. Somebody shook it after it cooled, and we saw precipitate. If we saw a precipitate, we would assume that the excess dropped out of solution. So if we had 6 grams dissolved, and about 4.5 was the saturation limit, that's a difference of 1.5 grams. So if this went back to a saturated solution, from a supersaturated solution, we would expect about 1.5 grams of the solid to either crystallize out or precipitate out of that solution. So this is the kind of information that we can get from these solubility curves. They're very versatile in the types of information you can get out or how you can use them. And chemists find solubility charts or solubility tables very, very, very useful.